Hi everybody, so today we're looking at the periodic table. So I divided up this section into three parts. Okay, so first one is actually just looking at the periodic table and reading it. Second one is how do we measure or determine reactivity? And then obviously that's going to bring us into bonding types, ionic and covalent. And if you haven't heard of this before, don't worry about it. I'll be explaining it. I'll be explaining everything from scratch. And the final part then is I'm going to determine the different ratios and therefore the formulas by using the periodic table. Even if you have not seen them before, you should still be able to do so. Okay, so let's have a look. We go down here to reading the periodic table. Now, I can't stress this enough. I say it to my own students all the time, okay? You do not have to learn off this periodic table. There's too much there. There's way too much information, okay? You just need to be able to read it. Now, a few things to note here. You can see down here where there's usually the lanthanides series and actinide series or whatever they're called. I've ignored those. You don't need to know them for junior cycle science, and you don't need to know them for leaving certificate chemistry either. Okay, you can ignore them completely. However, you will see them in most periodic tables. Secondly, that thing that might be different, that will be different actually, in your log tables, is the numbers up here. Sometimes they're going to be, instead of having a 1 and a 2, 3, 4, 5, 6, and 7, 8, and so forth, they might be in Roman numerals. So you might see, instead of 4 over here, you might see IV, and 5, you might see V, and whatever. Okay, so just to bear that one in mind as well. The periodic table, when you're seeing it in your log tables, will not be in colour either. Okay, let's have a look. How do we go about it? Well, the periodic table is divided up into two sections. Well, I suppose more than two sections, but generally that's what we class it as. When you're looking at your periodic table, it's going to be white, okay, and black. So you're going to see two parts. You're going to see a line going down here, a zigzag line like this. Okay, and basically what that means is everything to the left of that line, or that ladder, I suppose. So everything over this side of it, okay, is a metal. And everything to the right of it is a non-metal. Okay, so just to bear that in mind, you can see so that the vast majority of the periodic table are actually metals. Um, there's tons of them. Okay, so we have that part done just to determine there's two sections to it there. Okay, and you'll see that zigzag line on your periodic tables fairly clearly. So I'm actually going to get rid of that now. Oh, I don't know how I did there now to that. You know what, I can just undo it altogether, it might be faster. Okay, now we have it determined whether it's a metal or a non-metal. Next, we have to determine what each of these actually mean. Okay, and where do we go from there? So first off, okay, if we're looking from left to right, like so, we call these periods. And we'll just do a different curve for that. So periods there. So periods go from left to right, as you can see there. And if we're looking downwards, maybe you might use a different color pen for this. If we're looking downwards, okay, we call these groups. So it's divided up into periods and groups. And just a reminder there that everything on the left of the side here is a metal, everything on the right of the side is a non-metal. Okay, this is just stuff you need to learn off. Now, what else do we need to know? Well, we need to be able to read groups in a lot more detail. Okay, the periods, not so much. The groups, however, we do need to know. Okay, so we'll start off with those there, and we'll get rid of the periods here now. So, what do we need to know about the groups? Well, you need to know the names of certain groups. There's a few in total that we need to know, and I'm going to mark them out here. So we have this one over here, group 1, group 2, group 7, and group 8. Sometimes there's a 0 there instead of an 8. I'll explain that in a moment. So look, let's start off group 1. group 2, group 7, and group 8. And this will bring us into the next section in a moment. So group 1, the name of it, okay? You just need to turn it off. They are known as the alkali metals. Group 2, alkaline earth metals. Group 7, halogens. And group 8, the noble gases. Now, there are other names for the rest of them, but you don't need to know them. You only need to know groups 1, 2, 7, and 8. Okay, so 1, 2, 7, and 8. Okay, so you need to know the names of those. So we've done a few things now in terms of reading the periodic table. First off, we know everything to the left of the zigzag line is a metal. Everything to the right of it is a non-metal. Secondly, we know that there are periods going from left to right of the periodic table. And thirdly, we know that that going in vertical lines, we have our groups. And our final part then that we've learned so far is the name of some of the groups. So 1, 2, 7, and 8. Alkaline metals for 1, alkaline earth metals for 2, and group 7 is halogens, and group 8 is the noble gases. And I'll discuss this in a little bit more detail in a moment. Now, we're not doing too bad, but can we further enhance our knowledge of these groups? Is there something else we can do to help us in our understanding? Well, there actually is. Okay, so in the previous video on the atom, when I was explaining that, and we discussed the Bohr diagrams, we discussed how many protons and how many electrons were there and so forth. But we can actually use the periodic table as to figure out the number of protons and electrons. We knew that already. We can use the periodic table to double check our answers to see if we're correct. And I'll explain that shortly, okay? For now, I'm just going to move on to the next part here, and then we'll go back to that. Okay, so measuring reactivity. And that brings us into bonding types, and there's two types, ionic and covalent. Now, a quick note here, guys. I'm not going to go into the bonding in a huge amount of detail. Okay, there's two types. Okay, and I'm going to explain these bonding types in a separate video. But for now, you just need to know the definitions. Okay, so ionic bonding is the attraction between oppositely charged ions, and covalent bonding is the sharing of electrons. Okay, so for now, you just need to know the definitions. Okay, now the only reason metals and non-metals or elements, atoms or whatever, okay, bond in the first place is so that they can become stable. They will not react if they are with one another. They are very unlikely to react, I should say. So they are very unlikely to react if they are stable already. So how do we determine if they're reactive or not? And is there a scale there? Are some elements, or I should be saying atoms in this case, are some atoms more reactive than others? How do we figure it out? Well, everything comes back to this guy over here, and that's the octet rule here. Okay, I'm going to highlight that there now. Everything goes back to that. The octet rule basically determines if an atom is going to be stable or not. So, what is it? Okay, I'm just going to write down my understanding of it. Okay, so the octet rule is, how can we describe it there? Is all atoms want to have a full outer orbit. Now, you can see how I'm linking this back to the previous video on the atoms in terms of in terms of the word orbit here. Okay, so all atoms want to have a full outer orbit. So let's just draw out one of them there. I think one of them we did was nitrogen. So we'll draw out nitrogen as 7 and 14 down here. And look, we're not going to spend a massive amount of time on it, but we'll do it right. Okay, so nitrogen, we draw a circle around us, our orbit. We know in the first one there it takes 2 electrons. We have a total of 7, so that's fine. And now we must draw in another orbit for the remaining 5 electrons. So 1, 2, 3, 4, 5. Because we know for a neutral atom, which this is, and you'd be told otherwise, that the atomic number, that's the number of protons in the nucleus of the atom, it's the same as the number of electrons. So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 electrons here. Now, there is the electron configuration that we have to take into account, okay, and that is our 2, 2, 8, 8, 2. The reason it goes up to 2 at the very end, guys, is because you only have to do the first 20 elements. So let's have a look over here. Is the most outer orbit, this one over here, is it full? And we can see clearly it's not full. Okay, if it's full, it has to have how many electrons? 8. Oct, meaning 8. Okay, so it's not full yet. It has 5 electrons in its outer orbit. It needs 3 more. So therefore, we can argue that nitrogen on its own, as a single atom, okay, is actually going to be unstable because it does not have a full outer orbit. Okay, and if they have a full outer orbit here, they're going to be stable. And all atoms want to be stable. Okay, so we have 5 electrons here. Now I just want to bring your attention back to the periodic table there. Let's see nitrogen over here. Nitrogen is here. And to see what group it's in there, guys, and this is told on the periodic table, okay, it's in group 5. And I mentioned already I had a number 5 down here. Well, 5 also here, this 5 over here, also indicates how many electrons are in its outer orbit. So for nitrogen, there's 5. For phosphorus, there's 5 as well. And let's just test that out for now. And we'll come back to the octet rule in a second. Look, we can use this size here. Phosphorus is here, and we draw a circle around it. Awful circle. Okay, and I think there was phosphorus, if we're going back up to it here, there's 15 protons, and therefore there's going to be 15 electrons. So 1, 2. Let's draw in the next one. So 15 take away 2 is 13, so we've got loads left over. So 1, 2, 3, 4, 5, 6, 7, 8. So if we count that up, we now have 10 electrons. We need 5 more. So I'm going to draw in my my next orbit. There we go. And I'm writing my 5 electrons here. 1, 2, 3, 4, 5. It doesn't matter where they go as such. I try to spread them out as evenly as possible. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we'll just double check phosphorus up here, guys. Phosphorus is here, and 15 is the atomic number, and therefore it's also the number of electrons in the atom as well. Now, both nitrogen and phosphorus are in group 5. Okay, yes, phosphorus has more electrons, which makes sense. Okay, because it has the greater atomic number and so forth. Okay, but if we look at the similarities between them, nitrogen has 1, 2, 3, 4, 5 electrons in its outer shell, or its outer orbit, I should say. And phosphorus has 1, 2, 3, 4, 5 electrons in its outer orbit as well. And both of them are in group 5. And it wouldn't matter if I kept going down here, guys. Every one of these elements are going to have 5 electrons in its outer orbit. If I go over here, each one of these elements here have 2 electrons in their outer orbit. So you can use the groups here to check if you're correct when you're drawing out your board diagram, because it should equal to the same number over here for the outer orbit. Okay, so it's a neat trick to, not a trick, a neat way of determining if you're accurate or not. Now, let's get back to reactivity though. So we now know that all atoms want to be stable, okay? And for them to be stable, they need a full, I can't stress that word enough, guys, has to be a full outer orbit for it to be stable. So, and if they're not stable, that's fair enough, they don't have a full outer orbit. Well, if we look at the periodic table there, only one group here out of the entire periodic table is going to have a full outer orbit. And that's going to be group 8, which is known as the noble gases. And the reason it has a full outer orbit, if you look at it there, is because each of these here have 8 electrons in their outer orbit, except for helium. Helium has 2. But if we drew up helium really quickly, that's no good, 2 tick. He, we draw a circle around it, and then we put in our electrons there, and you can see straight away that helium will have a full outer shell, or orbit, I should say. Shells and orbits. Shell used to be the old name, basically, but it's inaccurate to say nowadays. We should be using the word orbit. So we can see we have 2 electrons there, and if we look at electron configuration, 2 means it's full, basically, for the first one. So helium's the exception there, but for the rest of them there, guys, you can clearly see that have 8 electrons. That's why there's an 8 up here. Sometimes there's a 0, but yeah, 8. So neon, argon, and krypton, and so forth, these all have a full outer orbit. Okay, that's why they're called the noble gases. Obviously gases because they're all gases, but noble because it means they're above fighting and reacting with one another. Okay, they're beyond that. They're noble as such. Okay, so that means every other element in the periodic table has to have some sort of reactivity there. Group 8 being the exception. So every other element there has to have some sort of reactivity. And I wonder, is there any difference in terms of reactivity? Well, like if you look at, I don't know, some videos online on YouTube and stuff like that, you'll see sometimes there's explosions for reactions. And then maybe when you're in chemistry class, you carry out a chemical reaction and there's no explosion. And it's actually kind of boring more than anything. Well, there is a scale there for reactivity. And there is a way of determining how reactive it's going to be. Okay, a golden rule here is the closer it is to becoming stable, the more reactive it's going to be. I'm going to actually write that down over here. And we'll get rid of these there now. So, note, here we go again. The closer something is, I'll get rid of that too when I'm at it. So the closer an atom is to being stable, I'm just going to do brackets there, full outer orbit, the more reactive it's going to be. Okay, so the closer an atom is becoming stable, the full outer orbit, okay, the more reactive it's going to be. Let's go back up to the periodic table. We'll be constantly coming back up to this periodic table here. Okay, so if we're looking at, let's just say for argument's sake now, we're going to look at boron here. We ignore these transition elements, by the way, guys. Just ignore them for now. We're only going to focus on groups 1, 2, and then 3, 4, 5, 6, 7, 8. Let's look at group 1 here, the alkali metals, and we're going to look at we'll say boron here, which is in group 3. Now, we have to ask ourselves, which one of those is closest to becoming stable? Well, if we look at the elements in group 1 here, they all have 1 electron in their outer orbit. So if they just lose 1 electron in their outer orbit, then they'll be stable. So for instance, if we did lithium there for argument's sake, okay, and I'm just going to do it down here briefly. So Li, lithium, is group 1 and it has 3 electrons. So I'll draw my circle around it. And I put in my electrons, 1, 2, and has 1 more. So we're going to be drawing another orbit. and we'll just throw it there just to keep it separate. Okay, so we can see there now that lithium has 3 electrons, okay? And if it loses this electron here, then it becomes stable. So if it loses that electron there, it now becomes stable because it has 2 electrons there. And if we look at the electron configuration, the first one, it's a 2 here, okay? So it's actually now stable when it loses that electron. So let's have a look at another one. Let's just get rid of this for a second. And we'll say, let's look at sodium, Na. Okay, sodium has 11 electrons. So sodium is here, guys, has 11 electrons. So I'm going to draw in my circle there. So we have 2 done already. So I must draw in my electrons now. So 2 from 11 is 9. So there's 8 can go in this one here because of the electron configuration. And therefore 10, and 10 from 11 is 1. And oh, that's no good. So look, I'm going to draw in my last electron here. Okay. I know it looks a bit bigger than the others, but it doesn't matter. Okay, again, we can see that we have 1 electron in its outer shell, which makes outer orbit, I should say. Apologies. Which makes sense because sodium here is in group 1. So therefore it should have 1 electron in its outer orbit. Now, again, if we remove 1 electron here, and you don't need to know how, you just need to know that it could be done, like so. It now becomes stable because you have a full outer orbit here, 8 electrons. It is easier for sodium, just as a reminder there, guys, it would be easier for sodium, if we think about it logically now, for sodium to lose 1 electron than it would be to gain 7 electrons. Okay, because it's just closer in that respect. So if we remove 1 electron, it's now stable. Grand. Okay, so therefore group 1 are going to be very reactive. Okay, and the reason they're reactive is because they're so close to becoming stable. Remember what I was saying down over here? The closer an atom is to being stable, full out orbit, the more reactive it's going to be. So if I pick boron now for argument's sake, and this is going to be my last example now for these, I think. We'll say boron now. I knew that would happen. So boron is in group 3, I believe. It is. It's over here. Boron has 5 electrons in total. So let's say 1, 2, and we now draw in the next orbit. And we know for the next orbit, max of 8, but we only have 5 in total. So 2 from 5 is 3. So I have 3 more electrons to put in. 1, 2, 3. Okay? Count them up. 1, 2, 3, 4, 5. It's fine. Okay? Now, boron has either to gain 5 electrons, 3 plus 5 meaning 8, so for full outer orbit, or it has to lose 3 electrons. So that can have a full outer orbit here. It's compared to hydrogen and lithium and sodium, everything in group 1 over here, which only has to lose 1 electron. So it'd be easier for boron to lose 3 electrons than to gain 5, okay, for the most part. Okay, so therefore, going back to it, group 1 are going to be far more reactive than group 3. And the reason being is because group 1 are closer to becoming stable than group 3 are. Again, the closer it is to becoming stable, that is, to have a full outer orbit, the more stable it's going to be. So group 1 is more reactive. And something you just need to learn off, reactivity increases going down a group. So reactivity increases going down a group. So sodium is going to be more reactive than lithium. Likewise, cesium here is going to be more reactive than rubium, potassium, and sodium, and so forth. So going down increases the reactivity. There's loads of videos online to show the reactivity there increasing. Generally, when the reactivity increases, the faster the reaction and the more explosive the reaction. Um, and you can demonstrate that in a lab handy enough with lithium, sodium, and potassium. Okay, so let's just do recap a few things here. We've had a look at reading the periodic table now. Okay, we know it's split up into metals, which is everything on the left is zigzag, and non-metals on the right of it. Okay, we have our groups going down vertical lines, and we have our periods, our horizontal lines. Okay, you need to know the names of some groups. Okay, not all of them, just some of them. Okay, and really there should be no excuse for not knowing those. Okay, you're learning it off. Um, Another thing you need to note that the number of the group corresponds to how many electrons there should be in the outer orbit of every single atom in that group or element in that group. Um, Bonding types. There's two bonding types. I'm not going to go into a huge amount of detail today, just to show you the definition of both of them, and I will be going over them in detail in the next video. Okay, so you can kind of ignore it for now if you want, because it does tie in with this chapter. The octet rule, though, is important. So all atoms want to have a full outer orbit so that they can become stable. Okay, and the closer an atom is to becoming stable, the more reactive it's going to be. So that's why group 1 is very reactive, whereas group 3 isn't. Arguably, you could say group 7. Group 7 just has to gain 1 electron. Again, as 7 electrons in the outer orbit, it is easier for it to gain 1 electron than it is for it to lose 7. Okay, if you just think about it logically. So therefore, the halogens in group 7 are also going to be very, very reactive because they just need to gain 1 more electron and they are stable. Okay, so we have an idea of reactivity. Generally, the far ends, excluding the noble gases, which are all non-reactive, the far ends are going to be more reactive. Now, what else have we got to say? The last part of it, I believe it is determining the ratios and the formulas. So this is really important. This question here actually is a 2019 question. So it's one of the first questions ever asked for the junior cycle exam. Okay, for first year. So that came up in 2019, and you're given a table here, and you're asked to attach a ratio here, and then put in the formula. They give you one already. They give you water here, and you're told the water there's two elements, hydrogen and oxygen here, and you're told the ratio that for every oxygen atom you have two hydrogen atoms, and therefore it becomes H2O. But before we get on to magnesium chloride and ammonia, let's figure out how do they actually get H2O from water. Okay, this is something we know off by heart, but where does it actually come from? So let's go back up here to our periodic table now. I'm actually going to get rid of a few things here just to keep things nice and simple for us. So we're dealing with hydrogen and oxygen. So let's just deal with oxygen first because it's on its own. Oxygen, which is this atom here, is in group 6. So how many electrons does it have in its outer orbit? It should have 6 electrons. And if you ask yourself this, how many more electrons does it need to become stable? Well, it needs 2 more electrons. The reason being is 6 plus 2 gives you 8, 8 being a full outer orbit, okay, for oxygen. So it actually needs 2 electrons. Now let's look at hydrogen. Hydrogen is over here in the alkali metals. Sometimes it's actually in the middle here, guys, okay, because hydrogen is actually a non-metal. But it does have, even though it's a non-metal, it does only have 1 electron, so that's why it's put into this group here, alkali metals. But hydrogen actually is not an alkali metal. That's why it's a different color. Often you'll see it in the periodic tables over here. Okay, but look, we're discussing hydrogen now. We don't need to worry about the alkali metals. Hydrogen is in group 1, as we can see here. Therefore, it has 1 electron in its outer orbit. And if we go into more detail on it, if we look at the atomic number, hydrogen only contains 1 electron, full stop, but it only has 1 proton. So therefore, oxygen, O, plus hydrogen, because oxygen contains 6, right, little 6 on top. Hydrogen contains a 1 and a 1, and if you add them up, you're going to get 8. which is what we want. We want 8 octet rule. Okay, so that's why it's H2O, and the ratio is 1:2. One oxygen is to 2 hydrogens. Okay, with that in mind, let's have a look at the next example. I think it was magnesium chloride, but we'll just double check. Ah, yeah, it was. Okay, you're told the elements, guys. Okay, even if you have never seen these before, and students, when they were doing this, they probably wouldn't have had. You can actually still figure out the ratio and the formula. All you need to do is be able to read the periodic table. So magnesium chloride, magnesium and chlorine. Okay, let's have a look for magnesium. Magnesium is over here, so it's in group 2. Okay, grand. And chlorine is in group 7 over here. Now, let's ask yourself this, and I'm going to write down both of them here. Magnesium and chlorine. So, magnesium is in group 2. And I'll just do a 2 over here. And chlorine is in group 7. Okay, so how can we figure out how many, what our ratio is? Now, this is a little bit tricky, okay? But let's just go to magnesium for a second. Okay, magnesium has 2 electrons in outer orbit, and it wants to lose how many electrons? It wants to lose 2, so that it can have a full outer orbit. So therefore, chlorine has to take those electrons. Okay, so magnesium wants to lose 2, and therefore chlorine has to take it. But if we look at it here, if we remove 1 electron, so that becomes a 1 now, and chlorine does take it, so chlorine now goes from a 7 to an 8, which is stable. Okay, chlorine is this chlorine atom here is now stable because of 8 electrons. It cannot take any more, okay, if it wants to be stable. But we have a problem. Can we see here? Magnesium still has 1 more electron present. But therefore, you're going to have to ask yourself, perhaps there's another chlorine. Okay, we know there can't be any other elements. It's just magnesium and chlorine. We just don't know how many. So if I just, for argument's sake there, I just put in another chlorine here. So we'll go say plus. Okay, and what happens there now? I remove, chlorine initially has 7, as we had here. Okay, and I remove this electron over here. And I now put it over here onto the chlorine. So it becomes an 8. So we'll say 0 there, even though it is full, which is indicating that's a full outer orbit. And chlorine is full, and chlorine here is full. So therefore, our ratio is going to be 1:2. So this is for your magnesium, and this is for your chlorine. So your answer is going to be MgCl2. MgCl2. Now that was a little bit tricky, okay? The hardest part there was for students to realize that there had to be more than 1 chlorine atom, because magnesium at the start wanted to lose 2 electrons. Again, it's easier for it to lose 2 electrons than it is for it to gain electrons. Okay, 8 electrons or 6 electrons, I should say. Okay, and we knew that chlorine here has 7, and that magnesium at the start has 2. Okay, so we can't put 2 onto 7 because that gives you 9. It can only get to a max total there of 8, everybody. Okay, so as soon as you lost 1 magnesium electron there, we had that to a 1. Chlorine becomes an 8. That's fine. But where is that magnesium last electron of the magnesium going to go? And therefore you can decide then that there was actually an extra chlorine atom there. So I'm just going to leave that there now, and we'll do another one. These just take practice. Sometimes they're trickier at the start than they are when you continue on. So MgCl2. So what I mean by that, when they're trickier, they might appear tricky at the start, and to be honest, they are to when you're starting off. But if you just leave it and you come back to it after a while, you will get a eureka moment. So look, last part here, ammonia. We know there's nitrogen and hydrogen in it. So I'll go back up here to the periodic table. Nitrogen and hydrogen. So where is nitrogen? Nitrogen's over here. We've used that loads today. And hydrogen is over here. So I rise up my nitrogen here, and I rise up my hydrogen over here. Now, how many electrons does is in the outer orbit of nitrogen? Okay, there's 5. We can see it there. There's 5 electrons here in the outermost orbit there. Okay, So I put a 5 here. And hydrogen has a 1. Now, you need to ask yourself this. Is it easier for nitrogen to lose 5 electrons, or is it easier for it to gain 3 electrons? Well, it's obviously closer to the gaining of electrons than it is of losing electrons. So it's actually going to gain electrons. Generally, as a rule of thumb, guys, metals, which is everything up here, tend to lose electrons, whereas the non-metals tend to gain electrons. Okay, and that's just a general rule of thumb. So nitrogen is what I'm trying to say there, wants to gain how many electrons? It wants to gain 3 electrons, because if it gains 3 electrons, it'll become stable. Okay, 5 plus 3 is 8. Okay, so if we add on 1 hydrogen to it, okay, it becomes 6. I'll rub that out and do it again. So we add on 1 hydrogen to it. Let's do a plus here altogether. It becomes a 6. Okay, we can get rid of that one there now. Okay, so we're nearly there. Let's add in another hydrogen. Okay, because we need 8 altogether. And each hydrogen contains 1 electron because it's in group 1. And if you look at it, not only is it in group 1, if you look at the atomic number here, it only has 1 proton, so therefore 1 electron. So we're nearly there. So what happens? This hydrogen loses its electron, and the nitrogen up here takes it, becomes a 7 now. No good, we need to add in another hydrogen now. So put a H here, and again that hydrogen had a 1. Okay, so what happens there? The nitrogen pinches that 1, it now becomes an 8. So we have our ratio here. Okay, so we have our nitrogen and our hydrogen. So we have 1 nitrogen, and how many hydrogens do we have? If you count them up, we have 3 hydrogens. Therefore, it's going to become NH3. So I'm just going to get rid of that there now, and I'm going to pop it underneath the answer over here. So nitrogen was a 1 and hydrogen was a 3 because it's 1 is the 3 there, and therefore it becomes NH3. And that's our answer. So again, these just take practice. Okay, they really do. And I'll be doing a few more over the next few videos just to practice these ratios and formulas. But they're not difficult. And once you do get the hang of it, you're sorted then. So look, just to recap there very briefly, we went through this lesson how to read the periodic table. We figured out how to measure reactivity and why atoms are reactive and so forth. We had a brief look at ionic and covalent bonding. Again, we're going to look at this in more detail in the next video. And then our final part there was to determine the ratios and the formulas from using the periodic table. And again, when you're doing an exam, you're probably not going to have seen the ratio or formula before, and you'll just have to figure it out. But you have to be able to read the periodic table. It's so important. Okay, guys, look, I hope that lesson helped you in terms of your studies, and best of luck with it.